Greetings everyone, I am Armaan and today I'll be presenting the Banach-Tarski Paradox. This paradox is all about creating two identical objects of the same size and same density just from one. This may sound surprising at first, but allow me to convince you. We'll be covering the following topics today. Almost all of the paradoxes that have been discussed today are keenly dependent on a single idea that how drastically the things and the basic operations and functions that are defined in the domain of finite numbers and finite sets drastically change when we go to the domain of infinity. We'll also talk about some miniature problems that build to our paradox, and then we'll obviously discuss the star of the show, the Banach-Tarski. Now, when we think about creating objects from thin air, all of us may be reminded of this fake chocolate illusion, which is nothing but someone very good at editing and video animation skills. But trust me, Banach-Tarski is an entirely different creature. Believe it or not, Banach-Tarski can help you create an entire new star just from using a pea and a knife and by cutting, no chicken. The paradox was proposed by these two gentlemen, Stefan Banach and Alfred Tarski. It states the following: can a ball be decomposed into finite number of point sets and reassembled so as to get two eyeballs identical to the original? And the paradox even proves it in affirmation. We begin with an important concept that is essential to mathematics, the idea of bijections or one-to-one correspondences. A bijection or one-to-one correspondence is a mapping between two sets that is both surjective and injective. An important result of constructing a bijection is that the two sets that are bijected to each other are said to have the same cardinality or the same size. The given diagram illustrates a bijection between the set of positive rational numbers and natural numbers. Next up, we talk about the notion of countability and uncountability. The given set is said to be countable if it can be enumerated. That is, we can construct a bijection from that set to the set of natural numbers. The set of rationals and integers are examples of such sets. On the other hand, we'll call it an uncountable set if we can't construct any such bijection with the set of natural numbers. Real numbers is one such set. A few interesting observations follow. First of all, the set of even numbers has the same cardinality as the set of natural numbers. This may sound surprising and counterintuitive at first, since there are technically half as many even numbers as there are natural numbers. But as it turns out, that's not the case. It's just a case of density. It is possible to draw a trivial bijection from naturals to even given by f of n equal to 2n. Next up, an important observation is that the open interval 0, 1 is uncountable. This can be proven by the famous diagonalization argument given by George Cantor. Also, the open interval 0, 1 has the same cardinality. Also, a bijection that we can draw from the real numbers to open interval 0, 1 is 1 over 1 plus e to the x. Next up, we discuss an important result of uncountable sets over countable sets called filling the gaps. Imagine you have a line or a curve containing uncountably many endpoints and just a gap of 1 point in it. What we wish to do is rearrange the points on the line so as to fill the gap. Now, a trivial idea might include that let's pick up another point from the line and put it in the place. But you have created another gap. Okay. We'll repeat this process 2 times, 3 times, 100 times, billion times. Turns out you're always left with 1 point. How about an infinite number of times? As it turns out, we can actually do this. For every gap, there is one and only unique point on the line that you can fill it with. In fact, let's take points that are at 1 unit distance from the gap. We never run out of points, never run out of gaps because they are infinite. We just fill the line using bijections. That is why the concept of bijection is so core to this paradox. We can extend a similar idea to other curves. For example, a circle with a gap. Applying the same idea, so a circle also consists of an uncountably many points. We can just use countably many points on that and still apply countably infinite points on that and apply the same idea to get a complete circle. Just as the animation shows. We will now be discussing some miniature ideas and miniature problems that were key steps in our building blocks and paradox. It's important to go through some notation first for this section. We will define A, B, C, any letter which denote an action. A inverse as the reverse or the inverse of the action A, which is just undoing the action or backtracking. Actions. Sorry? Are all actions reversible? Yes, all actions are reversible. Actions written in an order will be calling as a sequence of actions. Epsilon will denote the empty sequence, that is, no actions at all. By definition, A inverse and A inverse A will be equal to the empty sequence. We'll call a valid sequence a one that is valid and does not contain any action and its inverse consecutively. We'll denote S of A as the set of all valid sequences that begin with the action A. We now talk about this very interesting set, this very interesting collection. It is the set of all possible strings that can be, all possible valid strings that can be created using the letters of English alphabet. It will be an infinitely infinite set, but a point to note is that it will be a countably infinite set. If we arrange all the words in that set in a dictionary, in a lexicographic manner, we will obtain what's called a hypervector. It's going to be infinitely infinite, obviously, and contain everything that will be happening in any of our lives and everything that won't be. This is a preview of how the hypervector is going to look like. Infinitely infinite. A crazy idea is to publish the hypervector. I mean, it's going to take an infinite amount of patience and paper to do so, but anyways. One thing we can do to publish the hypervector is to decompose it into 26 volumes, one corresponding to each letter. Every volume of a letter A will contain the right letter on the first page, along with all the words beginning with that letter inside it, but with the leading letter removed. That means, for example, if a reader has to read some word in a given volume, they must remember to add the first word on the cover page of that volume to that word. That means a reader reading a word BCB in volume D is actually reading the word DBCB. Now I want you to consider volume A. Every word inside volume A is definitely present inside the hypervector by definition of the hypervector. But on keen observation, what we observe is that every word present in the hypervector is also in volume A. If we just reduce the hypervector to 1/26 of its size, we save so much paper. This is another example of one-to-one correspondence or bijection. This is just like how even numbers are half as many as natural numbers, but still the same size of them. A cute animation just demonstrates what we did. So that's the thing. Next up, we talk about free groups and rotation groups. For actions A and B, along with their defined inverses, we call the free group of A and B named by F, A, comma B, and it is a set of all possible valid sequences that can be constructed using the actions A, B, A inverse, and B inverse. If we observe, it will clearly be the unions of sets S of A, S of B, S of A inverse, S of B inverse, and the empty string. Now, consider the following. Consider the set S of A. We will do a similar idea that we did for the hypervector. We remove the leading A. Clearly, removing the leading A in the set S of A does not add or subtract anything new to the number of elements, so it still remains same in size. But removing the A and picking it out, what we did is just create a copy of the set S of A along with some extra things, that is S of B inverse, and the empty string. We define A inverse S of A as what we just created. Now substitute this definition into the free group and magic. You just created another copy of the free group without using less than half of its elements. Repeat that for B. If we just create two copies of the free group without only using one copy of it, we are heading in the right direction. Now let's define a rotation group. Consider the set of consider the 3D sphere and fix two axes along it. Now we'll denote the actions A and B as rotation about these mutually perpendicular axes and their inverses and the rotation about the opposite direction. We now define what's called a rotation string. A rotation string will be a valid string that will be made up of these actions A, B, A inverse, and B inverse. For simplicity, we'll call the actions A as rotating it right, A inverse as left, B as up, and B inverse as down. And every action will cause a rotation of cos inverse 1 by the angle of cos inverse 1/3 in the corresponding direction. Now what I want to do is choose a starting point, any point on the sphere, and apply every possible rotation sequences on it. Note that we'll rotation string on it. Note that we'll be reading the rotation strings from right to left. This will come important at a later stage. Now, after applying every rotation, we obtain a set of destination points. We'll label each destination point by the sequence which leads us to it. A few key observations have been made. The starting point will obviously be denoted by the sequence by the empty string epsilon. Every rotation string is a way of rotations to reach a given destination point, which is actually a sequence in the free group of AV. Note that there are only countably many strings, and uncountably many points on the sphere. So clearly, no point. We will not be able to hit all the points, but we'll come to that later. On key observation, we find that the free group of AV is isomorphic to the set of rotation strings. We'll refer to the set of rotation strings from now as the rotation group. The existence of this isomorphism is a very important idea and will help us apply the same construction that we applied to the free group to the rotation set of rotation strings. This animation will make things clear. This is a left rotation, left rotation, and a downward rotation. It will be denoted by the sequence DL. We are now finally there. Let's set up the paradox. We consider all the notations defined previously, the rotation group of R, L, D, and U, with right and left being the inverses of each other and up and down being the inverses of each other. Now fix a starting point and do what we did. Apply every from the free group from the free group. Apply every possible sequence to get a set of destination points and label the destination points with the sequence that leads to them. Since there are only finitely many points, finitely many sequences, we'll cover finitely many points, just like the previous case. Now, next, what we want to do is we want to color every destination point by the final rotation of the sequence that leads us to them. The final rotation will be the leading letter in the sequence which leads to them. That is why we read it from right to left. We'll use the following color notation: left is purple, down is blue, right is red, up is orange. The set of points that can be reached from a given starting point, we'll call it the orbit group by these operations. So what do we do about the problem of uncountability? The key thing to observe here is that every point on the sphere is the orbits introduce the orbits which are the set of points, orbit of a group, that is set of points which can be reached from a starting point. They induce a partition on the underlying sphere. So every point on the sphere is just a part of is a subset of some orbit with respect to some new starting point. So what we do is we invoke the axiom of choice and choose a new starting point. We repeat the process until no point is left unlabeled and uncolored. Since there is no empty sequence over here, we label the set of all starting points. We color the set of all starting points with green. At this point, we have colored every point once, exactly once, except for what the codes call the poles. The poles are points on the sphere such that they can be reached in multiple ways and multiple sequences can reach to them, and they can also lead to themselves. They will be labeled in different ways and colored in multiple colors. Note that there are only 2 points for every sequence, which are the north and south. And since there are only countably finite many sequences, there are only 2 poles per sequence. That means there are countably finite poles. We will count these poles separately and label and color them yellow. And don't forget the starting point, we'll color that white. At this point, we have colored every point on the sphere in some color and in exactly one color. And we will now break it up into pieces. That's the right piece, the left piece, the down piece, the up piece, the set of starting points, the poles, and the center. Now I want you to pay very close attention here. The magic is about to begin. Don't blink an eye or a new star might be created. I want you to consider the left piece. Let's just rotate it right. Clearly, just in the case of rotation groups and free groups, it does not add or subtract anything new to the points. But by rotating it, we managed to create another copy of the left piece with a copy of the up piece, down piece, and a set of starting points. What we now do is add the set of at the right piece and the poles to it, poles and the set of poles and center point to it. And we have obtained another copy of the sphere with leftover elements. This is what we did with the left piece. We rotated it right. What we obtained was another copy of the left piece, the down piece, the starting points, and the up piece. So we managed to create one copy of the sphere with leftover pieces. Let's go to the second copy. Next, consider the up piece. Here we'll do a slightly different. I want you to remove all the points that are just a sequence of finite u's, that is u, etc. We call the set as u dash. I want you to remove all these points from the set of u. This is because what we wish to do in the next step is we'll create extra points that we already have, which we don't need. So we'll just remove these points. Now, from the leftover piece, we call it B. We now rotate B downwards. Again, this does not add or subtract anything new, so we still have the same number of points. Rotating that piece down gives us another copy of the up piece, not including the set U dash, and a copy of the left piece and the right. Add the points U dash back to it, the down piece, and the set of all starting points. And what you obtain is almost a second copy of the sphere, but you don't have the poles and centers. But here we arrive at a problem. We are out of points to cover. What do we do now? Remember the filling the gaps idea? The poles and center are actually just countably many points among uncountably many points. So what we can do is consider curves around the sphere which are non-intersecting and cover these gaps and apply filling in the gaps. And voila, you got another copy of the sphere. And that's Banach-Tarski Paradox. So what's wrong here? Is our math broken? What's wrong? Where did we go wrong? The traditional resolution to this paradox is measure theory. This paradox clearly violates some basic principles of the measure theory. The fact that the volumes of subparts must add up to the volume of total. Pieces that we created over here are infinitely complex. They don't follow measure theory and are said to be immeasurable according to the nearest theory. More on to that later. The non-traditional resolution that I will be focusing on over here and has been discussed from the previous paradox is the over-dependence of this paradox on the existence of axiom of choice. Many mathematicians consider the axiom of choice is a very important step in the proof of this paradox. Many mathematicians and scientists consider this paradox to be a reason to discard the axiom of choice. We know that the axiom of choice is independent of the ZFC axioms. So a few resolutions might include, one resolution might include is to take weaker versions of the axiom of choice that are strong enough to give a sense of axiom of choice, but weak enough to prove Banach-Tarski. To not prove Banach-Tarski. On the other hand, if we consider systems in which the axiom of choice is not allowed, the sets will now be measurable according to the measure theory, but we can't construct them in the first place because there's no axiom of choice in the first place. Still, this paradox is only possible in your brains and not in reality. I mean, of course, you can't cut a bee with a knife to create a sun. Banach-Tarski still remains a very forceful illustration in mathematics to denote the counterintuitive nature of sets and how things drastically change when you go to the domain of infinity. I'd like to end by reassuring you that we don't need to change our idiom to that. Thank you.